Hey everybody, welcome back to the channel. Neil here. Thanks for joining me for this video where we're going to be talking about atomic mass. Now, if you're studying chemistry, you've no doubt seen this type of question. Basically one where they give us a bunch of isotopes, they tell us the atomic mass of each individual isotope, they tell us the percent abundances, and the question is asking us to find the weighted average, or the atomic mass of the entire element. Well, this video isn't going to cover how to do that problem, because sometimes, unfortunately, we see a much more difficult variation on this question. And it goes something like this. Here are the isotopes. You figure out the percent abundances. Now, I know from experience this leaves most students scratching their heads, completely baffled by how to go about this. So this is going to be a short video where I just give you a step-by-step slow guide on how to get those kind of questions right. So if you're interested in that, stay tuned, like the video, subscribe to the channel, and prepare for that amazing feeling of relief when we begin to comprehend something that we previously thought was way over our heads.
Okay, so here's the question that we're going to tackle together. Let's read through it. Chlorine occurs naturally in only two isotopes, chlorine 35 and chlorine 37. Those are the mass numbers. Then we're given the actual masses of each individual isotope, and we're asked to find the abundances of each isotope. Okay, so herein lies the difference in solving this kind of question. Normally, we're used to getting the percent abundances, getting the masses of the individual isotopes, and using those to solve for the atomic mass. In this case, they're not asking us to do that. They want us to figure out what percentage of the chlorine in the world is chlorine 35 and what percentage of the chlorine out there is chlorine 37. So where does this process begin? Well, you can see in black, I've written out the general equation that we use to solve for atomic mass. And in that equation, we basically have our atomic mass set equal to the percent abundance of one isotope multiplied by its mass, and we're going to add that to the percent abundance multiplied by the mass of the other isotope. Now, if there were 5 isotopes, we would do that calculation in brackets 5 different times. I've only written it twice here because we're only dealing with 2 isotopes of chlorine. Okay, let's take a look at this number here, the 35.45. We're able to look up the average atomic mass of chlorine on the periodic table and actually use that. And we're not used to doing that, right? Because again, most problems want us to figure that out. But what you can see here is I just plugged that 35.45 in place of the average atomic mass. Now I've also gone ahead and plugged in the isotope masses that are given to us in the problem. So our two percentages become our x and our y, right? These are two unknown things. We need to figure out what they are. But if you're like me, you're probably confused on how you're supposed to solve an algebraic equation when there's two different things that you don't know. I mean, we're all very well accustomed to solving for just x or for just y in an equation. But how do we solve for two different numbers at the same time? Okay, well, these two numbers are not just any two numbers. You see, we're going to use the fact that they are percentages to our advantage. The truth of the matter is that these two percentages, x and y, well, when added together, they have to equal the number 1. Okay, why the number 1? Where did I get that from? Well, as you guys know, when you're dealing with parts of a whole in percentages, all the parts have to add up to 100%, right? But why am I not writing x plus y equals 100%? Because as you'll remember, in these calculations, our percentages are converted to decimals. And if you take 100% and you convert it to a decimal, you're just going to get the number 1. So in this case, x plus y has to equal the number 1 because 1 is the decimal or whole number representation of 100%. So now what I can do is I can go back into my equation and I can use this relationship to represent y in terms of x. What do I mean by that? Well, if I rearrange this equation and I say, well, I wonder what y is equal to, by moving the x from one side of the equation to the other, I would get this. Y is equal to 1 minus x. So that means I can go back over to my equation that I have written out, and I can replace this y with 1 minus x. And folks, anytime you are asked to solve one of these problems, I don't care what element it is, you're allowed to replace that second percentage that we would normally give the variable y with 1 minus x. And we're just going to keep the other percentage that we don't know, x. And now we only have one letter in this equation that we have to solve for, which is x. Okay, so let's rewrite this. And now let's do it in terms of x's only. We're going to get rid of that y. So we're going to have 35.45 is equal to x multiplied by 34.9689, and that's going to be added to now 1 minus x instead of that y multiplied by 36.9659. Okay, so you see how we did that? We got rid of the y, and now we only have the letter x to solve for. Okay, so what are we going to do first mathematically? Well, first, I'm going to figure out this part and this part. So I'm going to have 35.45 is equal to 34.9689x plus, now this gets a little bit tricky for some people. You have to remember when you're multiplying a number by an expression that's next to it, you've got to distribute the number to both parts of the expression. So I have to multiply 36.9659 by the number 1, which would just give me 36.9659. And then I have to put that minus sign in there. That's part of the 1 minus x expression. But now I have to also go in and multiply the 36.9659 by the x, right? So that's going to give me 36.9659x. Okay. So now we've gotten rid of those parentheses, and now we can start doing what's known as combining like terms. In other words, any number with an x after it can be combined with other numbers that have an x after it, and any regular numbers, and by regular I mean without an x after them, they can be combined as well. So the first thing I'm going to do is I'm going to combine this 36.9659 with this 35.45 because they're both numbers without an x after them. Now in order to do that, I've got to bring the 36.9659 over to the other side. So I'm going to do that using subtraction. And that will eliminate that number from this side. And then we're going to have to subtract it over here. And that's going to give us the number negative 1.5159. And that's going to be equal to 34.9689x. So now I'm just copying in everything that I didn't eliminate and this 36.9659x. Okay, great. Now we're going to try to combine these two numbers with x's, right? So that's the 34.9689x minus 36.9659x. And so we're going to rewrite this part because at this step we're not changing that number. And now we're going to go ahead and do this subtraction piece here, and that's going to give us a negative 1.997x. Okay, so now this is looking much simpler, much cleaner. And our last step is to isolate the x, the variable, the thing we don't know. Remember, that's going to be the percent abundance of one of our isotopes once we solve for it. So we're really close. So in order to do that, we need to do some division. So let's divide both sides by 1.997x. And oh, I'm sorry, actually, not the x, just the number. We want the x to stay there. And so that's going to get rid of the number on this side. And then over here, we'll have to do the same thing, 1.997 4997. Okay, and now we're going to figure out what x is. When I put in my calculator negative 1.5159 divided by negative 1.997, I get 0.759 is equal to x. That is my x. And if I round that, I can get 0.76 is equal to x. So what does this mean? Well, this means that x, which was the percent abundance of one of our isotopes, this is its percent abundance expressed as a decimal. Okay, but what is it as a percentage, right? Well, all I have to do is multiply by 100. 0.76 times 100 gives me 76%. And that is for x. Okay, so if we go back up here slowly, let's remind ourselves, what was that x again? Okay, so that was the percent abundance of this isotope. That's the 34.9689. So that's chlorine 35, right? So we just found out that chlorine 35 it has a percent abundance of 76%. Well, what does that mean for our other isotope? And by other isotope, I mean this chlorine 37. Well, that's just going to be the remaining piece, right? So we have our chlorine 37. And if this isotope was 76%, the chlorine 37 must have a percent abundance of 24% because, of course, the two of those have to equal 100% of the chlorine that's out there. Okay, so this is how you solve a problem where you're asked to find percent abundances. Once again, the key steps to remember are you can look up the atomic mass of the element in question on the periodic table just like I did, because if the problem doesn't ask you to figure that out, you have every right to look that value up. The other thing is, remember, you're going to represent your two percent abundances using a variable in common. So for example, x or 1 minus x. Now sometimes students will say, well, how did you know to put the x by the first isotope, the one with the mass of 34.9689, and the 1 minus x by the other one? What if I was to reverse that? What if I put the 1 minus x by the chlorine 35 mass and the regular just plain x by the mass of chlorine 37? It wouldn't make any difference whatsoever. Go ahead, try it. Switch those two variables around, put the x in the other place and the 1 minus x, still solve for x, and you're going to get the same answers. You're going to find that chlorine 37 is 24% and chlorine 35 is 76. And after that, it's really just math. It's algebraic shuffling, condensing things, combining like terms, and solving for that variable. Okay, now remember, this is only going to work if this is a question dealing with an element that has two isotopes. You're not going to see questions where there's 3 isotopes or 5 or 7, because then we wouldn't be able to simplify the variables into just the x and 1 minus x relationship. So this is only going to come up when there are 2 isotopes, and this is how you do the problem. Thank you guys so much for watching. I hope this made this process a lot easier for you. And if you have any questions about it, you need clarification, you can just drop a comment down below and I'll be sure to get back to you. Have a great day.